and that's slowing the planet down. So that's a way to understand, excuse me, why the planet is slowing down as it gets further from the sun. And then after it rounds the bend and is coming back, now there's a component of gravity, this gravity force. Part of it, there's a component of it that's in the direction the planet is moving, speeding it up. So planets slow down as they move away from the sun because the sun is partly pulling opposite the direction that they're moving. And they speed up when they're getting closer to the sun because now there's a component of the sun's gravity that's in the same direction that the planet is moving. And then the perpendicular component to that is what's responsible for curving the path. So part of the sun's gravity curves the path and part of it speeds the planet up when it's approaching the sun.
So what would cause us to go out like the string breaking? Like what would cause Earth?
Nothing. You can't break the gravity. Yeah,
what
nothing.
if like something came and hit, well, we would be dead if this happened, but what if something like came and hit us like a meteor?
Oh, well, yeah, well, nothing would be big enough to do that. But yeah, but if I have, like if I have a rocket, or well, if I have a spacecraft flying around the sun, if it fires its rockets, the rocket engine, the exhaust puts a force on the spacecraft and changes its velocity, and that is what allows it to change its orbit. It's like hitting it over and over again if you like, kind of continuously smacking it with a hammer. Okay. So, yeah, if you had something big enough smack into Earth, you could change its orbit, sure. Right. But we wouldn't enjoy the change in scenery, let's put it that way. Yeah. Anything big enough to significantly alter our orbit would be big enough to wipe us out as well, yeah, as a species. Right. So let's not go for that.
Okay. Thank you.
Can you explain escape speed?
So escape speed refers to how fast you need to go so that you will never return, so that your orbit will be a hyperbola instead of an ellipse, is what it comes down to. Well, strictly speaking, at escape speed, it would actually be a parabola, where you would be such that if something is moving the escape speed, so imagine Earth had no atmosphere, because that gets in the way. This works better on the moon. But if you took away the Earth's atmosphere, if you launch something at, it's approximately 25,000 miles per hour, or about 40,000 kilometers per hour upwards from the surface of the Earth, then it would never fall back down again. And in the limit, as it got infinitely far away from the Earth, the speed would get slower and slower and slower, so that in that limit, the speed would go to 0 when it was infinitely far away, which means it would take forever, but in other words, you would be giving it just enough energy to never fall back to Earth again. That's what the escape speed is. When you give it just enough energy to never come back down again. Now, sometimes people think that means, oh, so it's going to escape Earth's gravity. Well, you can't do that. Earth's gravity essentially goes forever, because 1 over distance squared, that never goes to 0. So you can't escape Earth's gravity. What it really means is you never fall back down again. Any slower than that, and eventually you would come back and fall down again. So it's not actually true that what goes up must come down. It's what goes up at slower than the escape speed must come down.
Thank you.
Would you please be able to explain just like one more time how radioactive half-lives and decay work?
Sure. So, it's so easy to do that. And so, as we wait for the thing to reboot, shut it down.
Where's that?
Yeah, this is my brain right now, apparently. But anyway, your brain is not doing this right now.
What did you ask? I'm sorry.
Oh, sorry.
Oh, half-life. Just wanted to ask about radioactive half-life. Right.
I need that.
Right. Radioactive half-life. So, while this is doing this nonsense, so, thing number 1 to understand is some nuclei are unstable, in that a neutron in the nucleus can spontaneously turn into a proton by giving off some particles, or a proton can turn into a neutron, which means it turns into a different type of nucleus because It's the number of protons that determine what element it is. So there are some nuclei of atoms that are inherently unstable, unlike, for example, say, like the air we breathe is mostly oxygen-16, 8 protons and 8 neutrons. As far as we know, an oxygen-16 nucleus, if you left it by itself and came back a billion years later, it's still there, it's still an oxygen-16 nucleus. On the other hand, if you take a potassium-40 nucleus and leave it by itself and come back later, there's a chance it will have decayed into argon-40. It will have had one of its particles in the nucleus change into another type of particle. I have to think about which is which by looking at the periodic table again, but it's actually not important for these purposes. There are some nuclei that are unstable. And such unstable, any given type of unstable nucleus, like potassium-40, is associated with what we call a half-life. And the half-life is how long it takes half of the remaining nuclei to decay, no matter when you start. In other words, if I at some point say, I'm going to start timing right now, if you wait for one half-life from the time you started, then the atoms of potassium-40 that were there when you started timing, after one half-life, half of them will have decayed into argon-40. And for some radioactive elements, for some radioactive elements, the half-life is microseconds or days or something like that. For potassium-40, it's 1.25 billion years. It's 1.25 billion years. So you'd have to be very patient to watch all of the atoms, or half of the atoms decay, I mean. But on the other hand, that makes it very useful to us because 1.25 billion years being the half-life means that there is enough time for it, that's long enough that we can use it to date how old the solar system is, because there's still some of it left in rocks that have been around since the solar system formed. So, now that I have this back, I can talk about it some more. As soon as that shows up there. So in class, is this the one? No, it's not this one. This one, chapter 8. In class, we talked about the analogy of using coins to represent this. So if I toss a bunch of coins in the air, then about half of them will land heads. And you can think of the ones as landing heads as being the ones that decayed, if you will. If you think of each coin as being like an atomic nucleus to represent it. If you say heads is decaying, then every time you toss the coins, then about half of them turn up heads, and you could take them out and say, okay, now the ones that came up tails, those are the ones that still haven't decayed yet. And so if I toss a bunch of coins, after one coin toss, of my original sample of coins, after one coin toss, half of them have decayed, if you will. After another coin toss, half of that remaining half will have decayed. After a third coin toss, half of the half will have decayed, and so forth. So every time you toss the coins, you've got another factor of a half involved. So after one coin toss, half the coins that you started with are left. After two coin tosses, what fraction of the coins you started with are left? On average, it's statistical, but on average, 1/4. After three coin tosses, what fraction are left? 1/8. After four coin tosses, and so on, and so forth. So that's the way radioactive decay works. In other words, after one half-life, half the original sample is decayed. After two half-lives, 3/4 of the original sample is decayed, 1/4 of it is left. After three half-lives, 7/8 of it has decayed, 1/8 of it is left, and so forth. And that's the key to using this to determine how old things like meteorites are, or rocks on Earth are. Because when a rock melts, it kind of starts the clock when we're talking about dating it with, say, potassium-40. Potassium-40 is very convenient because what it decays into is argon-40. And remember we said that argon-40 is a noble gas. It's a gas. And so if argon-40 is created in a bunch of molten lava, it won't stick around because it's gaseous. And so it's just going to find its way out and leave. But on the other hand, if you create an argon-40 atom out of a potassium atom in a rock that's already solidified, the argon atom will be trapped there. It won't escape from it. And so that means that if you can measure both the amount of argon-40 in the rock and the amount of potassium-40 in the rock, you can assume that all the argon-40 in the rock used to be potassium-40, and that the rock didn't have any argon-40 in it to begin with because it only started being trapped when the rock melted. So, for example, if I made measurements on a rock and I discovered that there was, that there was 7 times as much argon-40 in it as there was potassium-40, well, what we would be able to infer from that is that 7 out of 8 of the original potassium-40 atoms had decayed already, so that only 1 out of 8 of them was left. We would be able to infer that only 1/8 of the potassium-40 atoms were still left since the time compared to when the rock last solidified. And so how many half-lives have passed if 1/8 of the potassium-40 atoms are still there? How many half-lives is that? 3. If 1.25 billion years is 1 half-life, how old is the rock if we've determined that it's been 3 half-lives since it formed? I'm going to go 3 times 1.25 is 3.75 billion years old. So we can tell how old the rock is by what fraction of the potassium-40 atoms haven't decayed yet. What fraction of them have stuck around, are still there. And, you know, it doesn't have to be an exact number of half-lives. If we discovered that the fraction was, you know, like whatever this would be, like 0.33, you could either read from the table how old, read from the graph how old the rock was. Like, you know, if this value here looks like about 1/3 of it, I could go over here and say, oh, it's about 2-ish billion years old. Or you can do a relatively simple calculation and figure out the same thing. Hint, you know, on an exam, I would make it nice even numbers. Or at the very least, be where you could read it on the graph pretty nicely. You know. Yes?
Yeah, so that's what I was going to say, like on an exam, would you just put like, say 1 half-life at the top and then it's like, you know, 1, 2, 3, like basically.
I'd be likely to do something like that, or make it where it was really easy to tell, like, you know,
yeah.
just, you know,
And
you know, it'd be something where if I gave this as a multiple choice, there'd only, you know, if it was 1/3 of it was left, you know, that'd be about right here. If I gave it as a multiple choice, if you know what you're doing, you would know that the distractors, which is the fancy name for the wrong answers on a multiple choice question, if the distractors are 1, 3, 4, and 5 billion years old, and one of the answers is 2 billion years old, you'd be able to tell, oh, it's got to be 2 billion years old because 1 billion doesn't make sense. That's nowhere near 1/3 of it's left. 3 billion, that doesn't make sense. There's less than 1/4 of it left, and so forth.
Oh, I see.
Right. In other words, if you know what you're doing, only one of the answers would make sense.
Yeah.
As opposed to, you know, if I'm giving this to physics students, I'd want them to say, oh, it's 2.243 billion years old with their calculator or something.
I just didn't know if you were going to give us the fraction of the isotope and then ask the years, specify the years, and see how many
I could do it. It could go either way, but if you understand it, you know.
Yeah.
I mean, you know, I could
you
also
ask, well, I'm sorry, so, like, if you were to reverse the question and say, okay, so 1 half-life is at half, you know, where would 3 half-lives be? And we could give you obviously a rough approximation.
Yeah, or if I said, you know, the rock is, you know, I mean, in principle, I could say something like, you know, the rock is 3 billion years old, what fraction is left? Well, then you'd say, okay, it's 3 billion years old, so the fraction that's left is somewhere between 0.125 and 0.25, you know. And you could estimate, here it looks like about 0.2-ish, you know, or something like that. And again, the distractors, you know, I'd make it so, you know, it would be mean if I, you know, if it was like something like this and I said 1.9 billion, 2 billion, 2.1 billion, you know, that would be like, what? You know, then you'd need a calculator.
Yeah.
But I would give you, if you know what you're doing, you'd be able to figure out the only one that makes sense is this one.
Yeah.
That's what.
Yeah.
Does that make sense? Okay.
An isotope is when it's,
The
sorry,
number of neutrons.
neutrons is different.
Yes, the number of neutrons is different. So the identity of the atoms is based on the number of protons. So it's the number of neutrons that differs from one isotope to another. Carbon-12 has 6 protons, 6 neutrons. The isotope carbon-13, 6 protons, 7 neutrons. They're both isotopes, right? So these two isotopes of carbon, one has 6 neutrons, one has 7 neutrons. But they both have 6 protons. That's what makes them carbon.
Okay.
Yes. Did you have a question?
Can you go over frost lines just in general?
Go over
Frost line?
frost line, yeah, sure. Any other questions about this stuff? Okay, so frost line, yes. So, oh, I almost pushed that button again. Stop. All right. So anyway, oh, conveniently, same presentation. So the solar system formed from the collapse of a cloud of interstellar gas and dust. The gas was almost all hydrogen and helium. 90% of the mass was in that hydrogen and helium, but it wasn't available directly for planet building. Planet building starts, and for that matter, planet building starts with accretion, with microscopic particles of dust sticking together, colliding and sticking, and then building up bigger and bigger particles and so forth. The crucial thing about the frost line is, so there was a nice warm proto-sun forming in the middle of this proto-solar nebula, the protoplanetary disk surrounding it. So where was it going to be warmer? Towards the sun or far from the sun? Duh, right? It's going to be warmer towards the sun, right? Now, we kind of conveniently divide the stuff that ain't hydrogen and helium, the molecules in there that can make up the little dust specks potentially, into 3 categories: rocks, metals, and ices, also called hydrogen compounds, which is mostly methane, water, and ammonia. Okay? So rocks, metals, and ices. So at very high temperatures, they all stay gaseous. Now imagine you start cooling things down. So close to the protostar, close to the protosun, everything is gaseous. Metals are gaseous, rock is gaseous, ices are gaseous. But as I move further from the protostar, the protosun, things are starting to cool down. What's the first things that start to condense as the temperature cools? Is it rocks, metals, or ices? Metals, yeah. Metals have the highest condensation temperature. Get below around 1500 Kelvin, which is pretty toasty by human standards, and little metal flakes start to condense, to solidify out of the nebula. So closest to the sun, only metals can condense. We keep going, and then what's the next thing that can also condense? Rocks. Now, can metals still condense out here? Yeah, right. So it's not that now it's rocks instead of metals, it's rocks and metals. Okay? And eventually I get to the point called the frost line. And the reason it's called the frost line is because, well, what is frost made of on Earth? Ice of what molecule? Water, right? Water is one of the ices. Well, you can also, under the right conditions, you could make frost out of methane and ammonia, because methane ice and ammonia ice look a lot like water ice. Visually, they don't look very different. They wouldn't taste the same for sure, but they look similar to water ice. So the frost line refers to this basically it'd be a circle around the sun because it's in this disk. Beyond the frost line, it was cold enough for ices to condense into solid form. And the significance of that is that even though hydrogen and helium are by far the most common components in the nebula, by far, the second most common, I'm trying to remember if I did have the slide that said this, I'm sure I did. The second most common component, is the ices, is the hydrogen compounds. So that means that because you needed solid grains to start with to start forming planets, past the frost line you had all of this stuff to build planets with. And in particular, the ices, because they're the most abundant, add a lot of planet-building material on the outer part of the nebula, part of the disk, compared to in the inner part where we've only got rocks and metals. So one of the things we're supposed to explain is why are there terrestrial planets that form close to the sun, which are rocky and metallic, and then Jovian planets far from the sun, which have a lot of hydrogen and helium? And the answer, according to solar nebula theory, is in the inner salt part of the nebula, ices couldn't condense, and so as a result, the planets that got built were made of rocks and metals. Beyond the frost line, there was a lot more material available, and so the protoplanets that formed by accretion out there were more massive because they had a lot of hydrogen compounds to be built with. But that's not the whole story, because also they got big enough, like 10 or so Earth masses, that they could also then have enough gravity to start pulling in hydrogen and helium, which was by far the most abundant material. And so Jupiter and Saturn grew very large because they started as big planetesimals with lots of ice and rock and metal in them that then got massive enough for their gravity to start eating, so to speak, hydrogen and helium gas, which by far was the most abundant material. And so it's like, then they were like, oh man, let's start chowing down. And so then they grew very massive because now they had access to the most abundant material in the disk, which was the hydrogen and helium gas to build themselves out of after that. Yes?
So then what considers a planet dead? Like I learned about it in the book, but isn't there certain planets that are like dead?
Geologically dead,
Yeah.
So I'll answer your question as soon as I verify. So does that help? Okay. Any other questions about that? Okay. So is Earth geologically dead?
No.
Nope. How about Venus? You'll know that more when we cover the whole of Chapter 9. But Venus we haven't seen one erupt, but Venus we're almost sure has active volcanoes because it's got sulfuric acid clouds, and the only place you could get sulfuric acid clouds from is from volcanoes. Even if they erupted a few tens of millions of years ago, the sulfuric acid clouds couldn't be hundreds of millions or billions of years old. They would dissipate by then. So at least relatively recent, Venus's volcanoes have erupted, and they probably still erupt. There's no particular reason to think Venus isn't still geologically active. Okay, what about the moon? Is it geologically active?
No.
It is not, right? It has craters that are billions of years old. We know this because we have samples from the cratered highlands brought back by the Apollo astronauts who went to the moon. What about Mercury? Mercury looks a lot like the moon. Mercury is also geologically dead. We don't